In this video, we're going to be discussing executing certain algorithms on graphs. So we've already claimed that a connected graph is Eulerian. In other words, it has a path that includes every edge exactly once. If and only if it has no vertices of odd degree, in which case it is possible to make an Eulerian circuit, it comes back to where it started, or if it has exactly two vertices of odd degree, in which case any Eulerian trail has to begin at one of them and end at the other. We didn't fully prove this result, okay? What we still needed to show was that if G has no vertices of odd degree, it admits an Eulerian circuit, and if it has two vertices of odd degree, it admits an Eulerian trail. We showed that if it has more than two vertices of odd degree, it just doesn't have one. Now, a bridge, remember, is an edge that if you deleted it would disconnect two components of the graph from each other. So the algorithm that we're going to present is known as Fleuries Algorithm, and it always produces these Eulerian circuits or trails. First step, if a graph has two vertices of odd degree, begin at one of them. If every vertex is of even degree, pick a vertex and begin there. If any edge that leaves that vertex is not a bridge, follow it and go to another vertex and delete the edge you just took. So as long as wherever you're standing has an edge that is not a bridge, do that, and it doesn't matter which one you do. However, if you ever arrive at a vertex and now every edge leaving that vertex is a bridge, follow one of them and go back to step 2. As soon as there are no more edges, the construction is complete. Now, because we delete one edge at a time, we're only going to use each edge at most once. And because we don't delete an edge, which is a bridge, until it's absolutely necessary to do so, this actually ensures that we can always access edges that haven't been used yet. Okay, so the way this is summarized is don't burn any bridges unless you have to. Follow a path by using edges that are not bridges until you have no choice, and then use a bridge. All right, let's do an example. We've copied the algorithm. Now let's look at this graph. If we look at the degrees of all of the vertices, 2, 2, 2, 3, 3, 2, 2, 2, 4. So this graph does have two vertices of odd degree. Okay. Now, regardless of which one you start at, let's suppose we were starting here. If any edge leaving the vertex is not a bridge, follow that. Don't follow any bridges. So whether we start here or here, are there any bridges? Yes. This edge right here is a bridge. If we were to remove this edge, I'd have two distinct connected components. So do not follow this edge. These edges, however, are not bridges. If I were to delete this edge, everything would remain connected. If I was to delete this edge, everything would remain connected. So let's start from this vertex and take out an edge that is not a bridge. Now we're here. Orange edges, by the way, have been used and should be considered deleted. From this vertex, there's only one edge. Now it's a bridge, okay? Because this was deleted, once we delete this edge, this vertex is now disconnected. But it was my only choice, so take it. Now we're here. There's only one edge, and this is now a bridge. As soon as this becomes disconnected, this vertex will be disconnected from the rest of the graph, but it's our only choice. So follow it. Similarly, this is now a bridge, but it's our only choice, so follow it. This is a bridge, so it's our only choice. Follow it. Okay, now I have two edges here. Neither one of them is a bridge. If I delete this, everything remains connected. If I delete this, everything remains connected. So these two edges are not bridges, so follow one of them. It doesn't actually matter. Let's go ahead and take the top one. Now we're at this vertex, and this is now a bridge. As soon as this is deleted, this vertex becomes disconnected, but it is our only choice, so take it. Okay. So now we are left with a subgraph, which is these edges here. These are the only edges that haven't been used. Now this is a bridge. If this were to be removed, this vertex would become disconnected from everything. But these two edges down here are not bridges, so follow one of them. Do not follow a bridge unless it's your only option. And now we kind of see how everything is going to complete. Work our way back up here. So starting at an odd degree vertex, only following non-bridges until we had no choice, we automatically completed an Eulerian circuit. Okay. Here's another graph. So what we're going to do is we're going to check what are the degrees 4, 2, 2, 2, 4, 4, 4, 4, 6, 6, 2, 2. So it does not have any vertices of odd degree. So we can begin wherever we want. Let's begin in that upper left corner. Now, are there any bridges? No. Okay, either one of these edges, if it were deleted, would not cause any disconnections. So we are free to pick whichever one of those two that we want. Let's just go ahead and take the top. Okay. Now we're at this vertex. Multigraphs, if there's two edges connecting the same vertex, those can't be bridges because deleting one of them will not actually change any connections at all. So these are not bridges, and neither is this. If this were to be deleted, I could still get all the way back around by a longer path, but there are no bridges. So from these three edges, pick whichever one you want. Let's just take the top one. Okay, still no bridges, so we could go back. Now, this is a bridge, because if we delete it, this vertex becomes disconnected from everything, but it's our only choice. So follow that bridge. Now we're here. We could now, none of the three edges connected to this were bridges, so let's follow this one. This is now a bridge, but we have no choice, so take it. This is now a bridge, but we don't have to take it, so don't. Okay, so do not take this bridge. Let's take maybe this one right here. Now this is a bridge, but we have no choice. Now this is a bridge, but we have no choice. Okay, now I have these three edges here. None of them are bridges, so take whichever one you want. Okay, still, now this is a bridge. Notice that since we've deleted all of these edges, we've already used them. Using this edge right here would cause everything to disconnect. So don't take that, maybe take this one. Now that's a bridge, so let's take it. Now this is a bridge, but we have to take it. Now I have these three edges here, so take one of them. I still don't want to use this bridge, so we have to go back. And now this is a bridge, but it's our only choice, so take it. This is now a bridge, but it's our only choice, so take it. Now we're at this vertex, and we have these three edges here. This multi-edge can't be a bridge. This one would be. If I removed this edge, this piece would become disconnected from this one. So do not take this edge, instead take one of these. I now have no choice but to come back, and now I have no choice but to use this bridge, and finally, the last edge. And we are back to where we started. Okay, so this algorithm said there are no vertices of odd degree, so pick any vertex you want, and now just follow a pretty simple procedure. As you go edge by edge, having effectively deleted the used edges, just ask, don't follow bridges unless it's your only choice. That's it. You'll always complete an Eulerian trail, and in fact, if there were no vertices of odd degree, you will end up back where you started. Next up, something called Prim's algorithm. Now remember that if you have a connected graph G, a spanning tree is a subgraph, which is a tree and contains all the vertices. A minimal spanning tree, if you had a weighted graph, is a spanning tree that minimizes the sum of all the edge weights of all possible spanning trees. Now, can we find a minimal spanning tree? We remarked earlier that if you have a connected weighted graph, as long as there's finitely many vertices, a minimal spanning tree does exist. Well, if it exists, can we find it? Prim's algorithm is a way to find it. Assuming you have a connected weighted simple graph. Okay, so it has to be connected, otherwise we can't find a spanning tree. It's got to be weighted, otherwise it doesn't make sense to ask for one. If you had multiple edges between two vertices, since all edges have weights, you would never connect those two vertices with anything other than the edge with the lowest weight. So any multigraph, just pick the lowest edge weights between any two vertices and turn it into a simple graph and do the problem on that. The first step is to pick any vertex you want. We're going to make three vertex sets, C, A, and D, for connected, adjacent, and distant. The only vertex that starts out connected is the one you picked. The things that are connected to it by edges are adjacent to it, so those go into your adjacent vertex set. and everything else goes into the distant vertices. So you've got your one connected vertex, whatever happens to be connected to it are adjacent, and everything else is considered distant. Okay, we're refining our notion of distance to three very broad categories: stuff I've already used, stuff that's adjacent to it, and stuff that is far away. So of all of the edges that connect vertices from your connected set to your adjacent set, pick the one with the smallest weight. If there are many, pick any one of them, it doesn't matter. Add this edge to your graph, to the spanning tree that you're building, along with the vertex connected to it. That vertex is now no longer just adjacent, it's now connected, so move it from your adjacent set to your connected one. Any vertices that were distant but are now connected to the one you just added are now considered adjacent. As soon as both your adjacent and distant sets are empty, you're actually done, because at this point, every vertex will have been moved to the connected set, and the only way that happens is by connecting it to your spanning tree. Okay, otherwise, go back to step 2. That's it. This is known as a greedy algorithm because in step 2, we look at all of the edges I could plausibly add, and I always pick the cheapest one. In real life, making a minimal cost thing isn't always just about doing the cheapest thing at every step, right? There's the famous Vimes theory of boots, that a cheap pair of boots might wear out so fast that you have to replace them more frequently and therefore be more expensive in the long run. So it's not always the case that the cheapest thing at every step produces the cheapest process in the long run. However, Prim's algorithm is a greedy algorithm. It says, always add the cheapest edge you can, and in the end, it will actually produce the minimal spanning tree. Let's work through an example. Here's the algorithm copied at top. Now here is a simple weighted connected graph, and we want to find a minimal spanning tree. So step 1, pick any vertex to begin with. So we're going to make our connected vertices white, the adjacent ones will be blue, and the distant ones will be black. We're just going to start with this vertex on the left. Okay. Now, since we're going to start with that as our one connected vertex to begin with, the ones that are connected to it are now blue for adjacent, but things that are not connected to our one selected vertex, they're considered distant. We're coloring them black for the moment. Now we look at all of the edges connected to our connected vertex. 10, 13, 14, 10 is the cheapest, so use it. Which means this is now considered a connected vertex. Now everything connected to this has to be considered adjacent, but they already were. So now I ask, of all of the edges I could use, what's the cheapest? 14, 13, 7, 11. 7 is now the cheapest edge, so use that. Which means this is now considered a connected vertex, which means anything connected to it is now considered adjacent. And now you look at all of the edges you have available, everything that is an edge that contains a connected vertex, 14, 13, 11, 12, 15. Okay, so of everything that's in there, the cheapest one was this 11. So we use that. Now this vertex is considered connected, which means this is now an adjacent vertex. Now we look at all of the edges emanating out of our connected vertices, 14, 13, 12, 15, 8, 5. 5. That's the cheapest, so use it, which makes this connected. Okay, there's really no way to add things to our adjacent vertex set. We've used them all up of the distant ones. Now this is the cheapest edge coming out of one of our connected vertices. So now this is considered connected. And of all of the edges that come out of any of our connected vertices, the 9 is the cheapest, so use that. This is now considered connected. There are no more adjacent or distant vertices, so we have actually made a spanning tree. The white vertices, that's all of them, with the orange edges, forms a spanning tree, and of all possible ways to do it, this is the cheapest. Note, it does not use all the cheapest edges. This edge of 8 was used even though it is of lower cost than maybe this 10 or this 11. So it's not just a matter of pick the cheapest edges from the entire graph. It's pick the cheapest edges that are connected to the things you've already picked. Okay, it's a pretty simple procedure once you get used to it. Just always add the cheapest edge you can that gets you a new vertex. Okay, in step 2, we're only looking at edges that connect to adjacent ones. If an edge goes between two vertices that are already connected, you don't consider it, which is why this 8 wouldn't be considered at any point. If you had already gotten all 3 of these vertices in, then since these two would be already considered connected, you just wouldn't look at this edge anymore. We're trying to make trees, which means we don't want to form loops. Okay, so only look at edges going from your connected set to your adjacent set. Pick the cheapest one, and you're always going to get your minimal spanning tree. So let's try it again. Well, let's start here in the middle. The vertices that are adjacent to it will remain blue. Everything else is going to be considered distant. So now I just look at the edges that connect me from connected vertices to adjacent ones. 105, 170, 160, 85, 100, 85. Take that edge, which makes this adjacent, connected. It would also make these two things now considered adjacent, but they already were. So now I look at all the edges connected to adjacent. 105, 105, 170, 160, 100, 110. This 100 looks the cheapest, so let's go ahead and take that. Which makes this now a connected vertex. Now that this vertex is considered connected, this one becomes adjacent. All right, now let's look at everything going from a connected vertex to an adjacent one. 105, 105, 170, 160, 120, 115. This is now between two connected vertices, so I don't bother. 180, 140, 185. We have two choices. There are two edges of smallest weight, 105, 105. Pick either one. Okay, it doesn't actually matter which one. Let's just pick this one because it's shorter on the page. Why not? Well, now that we've connected this is now a connected vertex. Anything connected to it becomes adjacent, but that doesn't actually change anything. And now we just repeat this procedure. Let's see, 115, 170, 160, 105, doesn't matter because it's between two connected. 120, 115, 180, 185. We've got a 115 and we've got a 115. So these two things are now lowest. It doesn't matter. Let's pick this one right here. Now this is considered connected. Anything connected to this would now be adjacent. That doesn't change anything. It looks like now I've got some 105s coming out. Okay. Earlier I picked this 115, so I know nothing cheaper than 115 comes out of any of the vertices I used to have. My new vertex has two 105s coming out of it, so let's go ahead and take that one. Okay, so we'll take this short little 105. This is now connected. Doesn't actually change what's adjacent, but now this 75 is an option, so take it. Connects this vertex, which makes this one over here adjacent, so there's no more distant vertices. Out of everything going to one of the blue vertices, the cheapest thing is this 90, so take it, which opens up the option for taking this 55. This is now connected, which opens up the option for taking this 60. Now everything's connected and we have made a spanning tree, okay, because we definitely connected everything. They all became connected vertices, and we did so by always choosing the cheapest edges. We executed Prim's algorithm. We have a minimal spanning tree. What about shortest path trees? So Prim's algorithm finds a minimal spanning tree, and the goal is to connect all the vertices with the lowest cost. So here's a problem that's similar, but not actually the same. At first, it almost seems like it is. We have a connected weighted simple graph G, and one vertex is designated as the special one. That's like our central vertex or our home base. What we want to do now is make a spanning tree. So it's got to connect from every vertex back to home base. But there might be many paths, okay, in the original graph. But we want to make a tree. And specifically, we want to minimize the paths from each vertex back to home base with the lowest possible weight of all paths altogether. So we need to connect everything to home base, but we want to do so with the shortest possible paths. So what's different about a spanning tree versus this shortest path tree is it does specify a specific vertex v prime and then makes the shortest path to v prime from everything else. Rather than the shortest or lowest weight tree overall, you want to make the shortest path to home base. Okay? It's not necessarily the same thing as the minimal spanning tree. So the special status that we're affording to home base makes this a subtly different problem, and we'll actually see an example where the two are different. Now, to find the shortest path tree, we're going to use something called Dijkstra's algorithm. So for a connected weighted simple graph G, as soon as we designate home base or a special vertex V prime, the shortest path tree can be constructed with Dijkstra's algorithm. It's a bit more complicated than the other ones, okay? Fleury's algorithm, very straightforward. Don't burn bridges unless you have to. Prim's algorithm is a greedy algorithm, so it's pretty easy to execute. Dijkstra's algorithm takes a bit more getting used to. So the step length is long enough that it's not practical for us to copy it every time we run the algorithm. So I do advise you to copy this down. So first, create a function. This function assigns weight 0 to home base. It's a function on the vertices. And for every other vertex, you start off by giving this function a really big value. It doesn't actually matter what it is. The value you give is the same to every vertex, and it's larger than the sum of all edges in the graph. A lot of sources will tell you to just label every vertex with a plus infinity. Okay? I don't like involving infinity if I don't have to. It just has to be a number bigger than the sum of all the edges. Okay? This value will change. This function is going to start assigning different values to different vertices. But at the beginning, what we're doing is we are vastly overestimating how far away vertices are. We're saying, what's the distance to home base? Well, home base is distance 0 to itself. Every other vertex we're overestimating by calling it super, super far away. So now what we do is we create sets of remaining edges and used edges. So to begin with, all the edges remain. The remaining edges is the entire edge set, and the used edges are empty. Okay. So as we construct our shortest path tree, remaining edges might get used, okay, and U are edges that are currently a work in progress. What's different about this algorithm is some edges might move back from the used set to the remaining set. Okay, this tree is not going to be built up in a strict way where everything you've done remains. It's possible to change stuff as we go. We're also going to create sets of vertices. We call them questionable and distant. Okay? Questionable vertices starts off just as home base, and distant is everything else. Questionable vertices are going to be ones that are in our tree, and they have lengths associated to them, but that might change later on, which is why I'm not calling it finalized, we're calling it questionable. Distant ones, however, haven't even been connected yet. Here's the main portion of the algorithm, okay? So to begin with, we have a home base, and we assign it a weight of 0. Every other vertex gets assigned a weight that is larger than all edges put together, a vast overestimate of how far away they are. We take our edges and we split them up into remaining and used. To begin with, it's pretty straightforward. All edges remain, no edges are used. Vertices got split into questionable and distant. Home base is questionable, everything else is distant. Now that we've initialized our algorithm, we can run it. Of all the questionable vertices, find the one with the smallest value of f. Okay? This is a vertex that might still be extended and is closest to home base. We're temporarily going to refer to this as A. Okay, and it might actually be the vertex V prime. It could be the same thing. We're temporarily going to call it vertex A. Now we run this procedure. Suppose we have an edge that's in our remaining set, and it connects our special vertex A that we just pulled out to some other vertex X. You compute the value f of A plus the weight of the edge connecting them. F of A represents the total distance to get to A. This edge has a weight to go from A to X. So of the total distance to get to A, we are adding the distance to go one step further. If that computation is bigger than the label already attached to X, go to A and then do this edge is bigger than an existing path to X. The potential path we just explored, go to A and then to X, is longer than one we already had. So don't use this edge. This edge is just gone. Okay? If going to A and then taking this edge to get to X is bigger than a way we already had, we're never going to use that edge. Delete it. It's gone forever. What if going to A and then taking this one extra step is smaller than an existing computation? Then there are two possibilities. Maybe X was labeled with m, that starting overestimate, or maybe it had been changed already and had a smaller value? Well, if we just went to a and then to x, and x was labeled with m to begin with, this must be our first path to the vertex x. Replace f of x with this new value. F of x is supposed to represent the length of the path to get there, and m was our vast overestimate. Going to a and then following this edge was a quicker way than the existing overestimate, so replace that value with this one. This is now our computation of the length of the path to get to x. Go to a and go to x, and it was a better way than we started with. So x is no longer distant, it's now questionable because we have added it, okay? We're also going to add that edge to our used set. So if we find the first path to a vertex x, take that edge and add it in and add that vertex x as well. This is now a questionable vertex. This is now a used edge. The other possibility is going to a and then taking that edge gives us a shorter path to x, but f of x was not m. F of x starts at m, but we've seen earlier steps it's possible to change the value. So maybe we found a quick way to get to x, and it's even faster than an already changed value of f of x. So we have found a new shorter path to the vertex x. Well, again, replace f of x with this new value. The value f of x is supposed to be the quickest way to get there, and we found a faster way because this total, go to a and then follow this edge, was in fact a shorter distance than the existing label. So change the label. But what you have to do, since f of x wasn't equal to m, it had already been added to the graph at some point. Delete from the used set of edges any edges connecting x except the one we're currently looking at. So we may have already added an edge to x. Get rid of it. Only use the edge that we just used. If it was a distant vertex, make it questionable and remove it from distant, but if it was already questionable, just leave it there. Now go through the questionable vertices, okay? So all we did so far, by the way, is of all the questionable vertices, we picked the one with the smallest value of f, we called that a, then we picked something connected to that and ran through this procedure. Once you're done with that, go through the questionable vertices. If some vertex has, if any of the vertices that are questionable have no edges connected to it, remove it from the questionable list. It's no longer questionable, it's actually like fully fixed. We know what we're going to do with it. If the set of questionable vertices is now empty, you must be done. If it's not, however, go all the way back to the first step and start over. Okay, so this is the algorithm. It's lengthy, it takes some getting used to. I do suggest copying it down. So, because it takes a full page, we're not going to be able to copy and paste it as we do examples. So do actually have this, maybe, take a screenshot, copy it by hand, whatever. But now we're going to work through some examples. Let's get to it. Let's use Dijkstra's algorithm to construct a shortest path tree rooted at the vertex A in this graph. Okay, so we start off, we initialize the algorithm, assign to the vertex A value 0, and assign to every other vertex something that is much bigger than any total path. So just looking at it, for example, I know I can get from A to E with a total of 16, 11, and 5. But I'm not thinking that hard. I'm going to assign A value 0 because I start there, and everything else I'm going to assign value 100. Adding up all of these edges is definitely less than 100. And as I've mentioned, many sources will tell you just label everything else with a plus infinity. Okay, so I've labeled vertex A with a 0, and everything else has a label of a vast overestimate of the length to get there, 100. Remaining edges are going to be blue, used edges are going to be red, and edges which aren't in either set will be deleted as appropriate. So we start off, remember, with every edge remaining and no edges used. So there they are, they're blue. Questionable vertices are going to be blue and distant ones are going to be black. Vertices that are neither questionable nor distant will be white, but remember that we start off with our home base as questionable and everything else as distant. So there they are. Okay. So here is our, key, remaining edges blue, used edges red, questionable distant and fully processed vertices blue, black, and white as appropriate. Let's pick a questionable vertex. There's only one, it's A. Pick an edge connected to this vertex. Let's compare f of A, 0 plus the weight of the edge, to the value f of x. So let's take a look at, for example, this edge. F of A plus this edge, 11, is definitely less than the existing overestimate of 100. So 0 plus 11 is smaller than 100. However, 100 is the initial overestimate m. So what that means is we found a potential shortest path to B. We're going to take this edge and use it, and we're going to add this vertex to the questionable vertices. We're also going to replace the label on B with 11. This is now our current shortest path to get there, is length 11. Maybe later we'll find a shorter one, maybe we won't. This is now a questionable vertex, this is a used edge. Okay, so here's where we are at this stage. Pick a questionable vertex. Let's just use this again. Pick an edge connecting to some other vertex. Well, our only choice is this one, 9, okay, and it connects here. Our new path is start at 0, add 9. That's a length to get to C. It's definitely smaller than our starting overestimate of 100, so we found a potential shortest path to get to C. So use this edge and make this vertex questionable and update this estimate of how long it will take you to get to C. We know we can get there with a length of 9. We've now used this edge, so it's red. This is now a questionable vertex, and this is our current shortest path estimate. So here is our graph at this point. But now notice we have a questionable vertex A that is not connected to any remaining edges. That means it's no longer questionable, it's fully processed. So this vertex is now not going to be altered in any way from this point forward, nor any edges leaving it. Now pick a questionable vertex. Let's pick C. Pick an edge connecting it to something. Let's take this one of length 8. This now gives me total length to get to C, 9, plus edge weight, 8. That gets me to C, to vertex E, for a total of 17. That's definitely better than our initial overestimate of 100. So that becomes our new estimate for the distance to get to E, and this is now questionable, and this edge is used. There we have it. Okay, so now I know I can get from C to E with 8, and I can get from A to C with 9. So if I were to take this path, I could get to E with a total of 17. And here's where we are so far. Now let's actually change focus. Pick one of the questionable vertices. Let's suppose we pick B. Let's consider the edge with weight 14. Well then, f of B is 11, and this edge weight is 14, and that would get me to vertex C. So we're going to compare f of B, 11, plus this edge weight, 14, versus the existing path to get to C, which was a total of 9. Well, 11 plus 14 is 25, bigger than 9. So this potential path is not actually better than the one we actually have. What that means is this edge will never be used, so we simply ignore it. Okay. Here's where we are. We're going to continue to focus on B. It's still questionable. There are still edges attached to it that are not used. In fact, there's only one. So compare f of B, 11, plus this edge weight 5. That gets me to this vertex. Compare it to the existing value of 17. 11 plus 5 is actually smaller than 17. We have found a better way to get to E. So what we do is we update this value with our new shortest path. Any used edge connected to E gets deleted. And it was already a questionable vertex, so that doesn't change. So this gets replaced with 16. This edge is being used instead, and this edge gets removed. Okay, so it's possible that this function value might get changed many times. Now, here's the state of our graph. There are no remaining edges connected to B, so it is fully processed. We don't have to worry about it. These are now our only questionable vertices. Okay, let's focus on C. It has only one remaining edge. f of c, 9, plus this edge, 6, versus our initial overestimate of 100. So we found our first path to this vertex. So we update the value with 9 plus 6, or 15, and this is now a questionable vertex because we have found a path there. Okay, C now has no remaining edges, so it is now fully processed. Here's the state of our graph. There's only two questionable vertices, so let's actually suppose we're starting at D and trying to get to E. That would be 15 plus 7. That is worse than 16. So we're not going to use this edge, so we end up just deleting it. Here's the state of our graph. This vertex is questionable, but it's only got used edges, no remaining, and similarly for this one. So in fact, everything is now fully processed, and we have found our shortest path tree. If we want to get from A to C, the shortest path is to do this. If we want to get from A to D, the shortest path was to do this. The shortest path from A to B, and the shortest path from A to E. This graph from our home base gives us the fastest way in the original graph to get everywhere else. Okay, so more of Dijkstra's algorithm. You begin with a connected weighted simple graph and a special home base. You initialize the process by assigning your home base distance 0 and everything else a vast overestimate of the distance. Edges are now either remaining or used, but you start off with nothing used and everything remaining. Vertices are either questionable or distant. The only questionable vertex at the beginning is the one you started with. Everything else is distant. Now you run the algorithm. Pick a questionable vertex and an edge. Look at where that edge goes. Compare the value of how far away my starting vertex was plus the one edge that goes to it. Compare it to the value of my an already existing distance to get there. And ask what's better, the new path or the one I already had. If the new path is no better than the one you already have, you're not going to use this edge and you can delete it. If your new path is shorter than the existing path, maybe you found the first path there if the existing value was your big overestimate, or you already had a path but you found a new one. If it's your first path there, you're going to use that edge, add it to the used ones, and that becomes a questionable vertex and update the value of your distance estimate. If you actually found a shorter path to something you already had a path to, update the value, remove the old connection to that vertex, and add your new connection to that vertex. At a certain point, you're going to have every edge either used or removed, and then the algorithm is done. And what you've done is you have found the shortest path from home base to everywhere else.